Samuel Arbesman, The Magic of Code: How Digital Language Created and Connects Our World. If someone asked you to name the great wonders of the world, you'd probably think of Machu Picchu, the Grand Canyon, or the Great Wall of China. But here's something that might surprise you. Code deserves a place on that list, too. Why? Because it opens up a portal to comprehending all the other wonders around us. Code has become the lens through which we explore everything else. Want to understand how galaxies form? Astronomers write simulations. Curious about ancient climate patterns? Researchers code models that analyze ice core data. As novelist Richard Powers put it, the computer is the supreme connection machine, and code is the language that makes that connection possible. Are you ready to discover this hidden wonder of the world? Then let's begin. Technology and magic. Picture this. It's 1770, and you're standing in the court of Empress Maria Theresa. Before you sits an extraordinary sight. A life-sized figure of a man in Turkish robes seated behind a wooden cabinet filled with gears, wheels, and clockwork. This is the Mechanical Turk, and when wound up, it plays chess with uncanny intelligence, moving pieces with its mechanical arm and defeating seasoned players. Audiences gasped in wonder. Was this magic, divine intervention, or something else entirely? What they were witnessing was perhaps the world's first computer, a machine that appeared to think. Computers were once connected with wonder. When Charles Babbage dreamed up his analytical engine, or when Ada Lovelace wrote what we now recognize as the first computer program, technology was still suffused with enchantment. But then something shifted. Disenchantment has certainly found its way into computation. We've moved from playful hackers tinkering in garages to cubicle-bound IT workers following corporate protocols. The rogue Silicon Valley spirits like Steve Wozniak, who built computers for the sheer joy of creation, have given way to big tech's algorithmic efficiency. But think back to the rise of early coding culture. Those first programmers weren't just writing instructions. They were casting spells, creating entire worlds from nothing but logic and imagination. Code was playful, generative, almost alchemical in its power to transform abstract ideas into tangible reality. As we stand on the brink of even more major technological disruption, with artificial intelligence reshaping our world, it's crucial that we reclaim that flexibility, creativity, and sense of wonder in computing. Because at its heart, code remains what it has always been: human imagination made executable, our dreams given digital life. Understanding code. Picture a beautiful alpine scene. Snow-capped peaks catching the morning light, crystalline air, valleys carpeted in wildflowers. The kind of vista you'd find on a postcard. Beautiful, isn't it? Well, until the 17th century, mountains were viewed as hideous and frightening. Travelers described them as warts on the earth's face. Some even requested to be blindfolded when crossing the Swiss Alps. It took the Romantic movement to teach us to see mountains as sublime and awe-inspiring, transforming our entire aesthetic understanding. Code is to our time what mountains were to the 17th century. Many of us haven't yet learned to see and understand its particular wonder. Appreciation begins with understanding. Code is essentially a precise recipe that computers can follow, but it's built on something far more elegant than mere instructions. At its foundation lies the work of George Boole, a 19th century mathematician who developed a system of logic based on true and false statements. For instance, "It is raining and I have an umbrella" creates a compound statement that's only true when both parts are true. Boole's insight was revolutionary. You could perform mathematical operations on logical propositions like these, creating chains of reasoning that could be mechanized. This Boolean logic became the beating heart of computing. Every decision a computer makes, whether to display a pixel, send an email, or calculate a trajectory to Mars, comes down to these fundamental true-false evaluations cascading through millions of logical gates. But here's where the magic of translation happens. When programmers write code with loops that repeat actions and conditional statements that say, "if this, then that," they're working in languages designed for human understanding. Compilers act as sophisticated translators, parsing this human-readable text and converting it into the binary instructions that processors actually execute. It's like translating poetry into machine language while preserving all the meaning. This translation process has evolved dramatically over decades. Early programmers had to write in machine language, pure sequences of numbers that directly controlled the processor. The earliest computer, Fortran, revolutionized this by letting scientists write mathematical formulas in something closer to normal notation, which the compiler would then translate into machine code. Modern abstraction has taken this liberation even farther. Today's programmers can focus on solving problems rather than worrying about where their data lives in memory or how storage is managed, because layers of translation handle these details automatically. Think of code as an intricate tapestry. Individual coding actions are simple, discrete, repetitive, like single stitches guided by Boolean logic. But woven together through layers of abstraction and translation, they create something shimmering and complex. All the software shaping our lives, from smartphone apps to hospital systems, emerges from these cathedrals of code, millions of Boole's logical operations working in concert. Building blocks. Everything you can see, touch, or breathe, from the delicate petals of a rose to the vast expanse of a galaxy, is built from the same fundamental components: atoms. Code works remarkably similarly. Like atoms, code serves as the building block of our digital universe. And just as atoms can create everything from butterflies to mountains through different combinations, code can create infinite possibilities. Your favorite app, the system that guides airplanes, even the software reading these words to you right now. This creative power comes from abstraction, that process we explored earlier in which complex operations get wrapped into simple, reusable packages. This becomes exponentially more powerful through something called open source software. Think of it as a massive public library, but instead of books, it contains millions of these code building blocks that anyone can freely access and use. Projects like Linux, which powers most of the world's smartphones and websites, represent collaborative efforts in which thousands of programmers contribute improvements over decades. This spirit of collaboration has deep roots. It began with Unix, an operating system created in the 1970s at Bell Labs. Unix was revolutionary not just as software, but as philosophy. Its creators shared it freely with universities, where students and researchers could experiment, modify, and improve it. This created something unprecedented, a culture in which knowledge was freely exchanged rather than hoarded. What emerged resembles the oral tradition of Greek mythology. Just as ancient storytellers passed down myths through generations, preserving essential elements while adding their own interpretations and flourishes, programmers began inheriting these digital creations, reshaping them, and passing them on. Each generation builds upon the last, creating an ever-evolving tapestry in which individual contributions become part of a larger, living tradition. In this way, code transcends mere technology. to become a form of collaborative storytelling that shapes our modern world. Mathematical art. If you're of a certain age, you probably remember the screensaver, those mesmerizing patterns that would dance across your computer screen when you stepped away. Flying toasters, bouncing geometric shapes, and swirling colors seemed to have a mind of their own. These weren't just digital eye candy. They served a crucial purpose back when home computers used big boxy monitors with massive cathode ray tubes. When a static image stayed on the screen too long, it would literally burn into the phosphor coating, leaving a permanent ghost image. The screensaver solved this by ensuring the display kept changing. What made screensavers magical was how they generated endless novelty through algorithms, mathematical rules creating digital randomness with increasing complexity. Though screensavers are no longer essential, that spark of mathematical creativity persists through creative coding. While programming with plain text commands is straightforward, creating visual effects requires translating abstract mathematical concepts into pixels and colors, a more complex challenge demanding both technical skill and artistic vision. This led to processing, a programming language made for artists and designers. Created in 2001 at MIT, processing made visual programming accessible using simplified syntax and immediate visual feedback. The creative coding community around processing has genuinely re-enchanted programming. Artists create whimsical graphics, simulate realistic snowfall and flickering fire, design intricate mandalas, build playable online Rubik's Cubes, and render entire virtual cities. These projects emerge where mathematical constraints meet artistic vision. One mathematical concept that's become particularly beloved in this world is the fractal, patterns that repeat at every scale, like the branching of trees or the jagged edges of coastlines. If you zoom into a fractal pattern, you'll find the same shapes repeating infinitely, each iteration revealing new levels of detail. Fractals prove particularly suited to coding thanks to their recursive nature. Using what are called Lindenmayer systems, programmers can describe complex natural forms with remarkably simple rules, generating ferns, saplings, and sunflowers from just a few lines of code. Scale this up, and you can create entirely procedurally generated forests. This procedural generation now powers the vast landscapes in video games, creating worlds too large for humans to design manually. From the rolling hills of Minecraft to the infinite cosmos of No Man's Sky, algorithms generate beauty from mathematical rules. Like those old screensavers, today's creative coding proves that artistry flourishes within limitation, transforming mathematical constraints into boundless creative possibility. Speaking in code. Remember the story of the Tower of Babel? Once upon a time, all humanity spoke a single language and could understand one another perfectly. Then came divine intervention, scattering people across the earth with different tongues, creating a cacophony where once there was clarity. The world of coding tells a remarkably similar tale. At its foundation lies binary, the original atomic language of pure ones and zeros that all computers ultimately understand. But today, it's become a babel of programming languages. Python slithering through data science, JavaScript animating web pages, C++ powering video games, and dozens more, each with its own syntax and personality. This linguistic explosion began with ENIAC, unveiled in 1946 as one of the first electronic computers. ENIAC was a room-sized behemoth weighing 30 tons, its programming done by physically rewiring thousands of cables and setting switches by hand. Women mathematicians would spend days reconfiguring the machine to calculate artillery trajectories or weather patterns, essentially rebuilding the computer for each new problem. This proved impossibly cumbersome, so engineers developed punch cards, stiff paper sheets with holes punched in specific patterns that machines could read. Now, programmers could write instructions by punching holes rather than rewiring entire machines. But punch cards still felt clunky. Enter Fortran in 1957, the first programming language that let scientists write mathematical formulas in something approaching normal notation. Instead of cryptic machine codes, they could type A equals B plus C, and the computer would understand. Fortran revolutionized scientific computing, enabling everything from nuclear simulations to early weather forecasting. Today's programming landscape offers extraordinary diversity: C++ for system software, Python for artificial intelligence, Lisp for symbolic reasoning, Perl for text processing. Yet remarkably, these languages share a fundamental property called Turing completeness, meaning any computation one can perform, another theoretically can too. Even Minecraft, the block-building game, is Turing complete, though you wouldn't use it to run spell check. This interchangeability masks profound differences in style and purpose. To understand just how varied programming languages can be, consider the world of esoteric languages. Programming languages created not for practical use, but as artistic statements or intellectual puzzles. Take Chef, where every program must read like a genuine cooking recipe, complete with ingredients and cooking instructions, yet still perform real computations. Or Whitespace, a language that ignores all visible characters and uses only spaces, tabs, and line breaks. These languages are Turing complete too, meaning they could theoretically run your banking software, though doing so would be like trying to perform surgery with a paintbrush. These linguistic experiments reveal something profound about the nature of computation itself. Each programming language becomes a different lens through which we can view and solve problems, some optimized for efficiency, others for readability, and some simply for the joy of creative constraint. A new frontier. We're living through a curious paradox. Our cognition and attention spans have adapted to computing technologies in ways that aren't entirely flattering. We skim rather than read deeply, multitask inefficiently, and find our focus fractured by constant notifications. Now, as artificial intelligence encroaches farther upon our daily lives, our capacity to think faces yet another set of challenges. But the early pioneers of computing took a radically different view. Rather than seeing technology as something that would stunt human cognition, they believed software and computing would transform and broaden our cognitive capacity. What can we learn from their vision? Consider Vannevar Bush, who in 1945 imagined the Memex, a mechanical desk in which scholars could store books, records, and communications, then retrieve them through associative trails that mimicked human thought patterns. Or Paul Otlet, the Belgian documentalist who dreamed of the Mundaneum, a vast repository of the world's knowledge accessible through networked terminals decades before the Internet existed. These visionaries understood something profound. They were part of a continuum of human knowledge organization that stretches from alphabetization to the Dewey Decimal System to indexing. Which brings us back to the humble index card, so fundamental to early programming. The technologies of the typewriter and index card ultimately converged in the personal computer, creating unprecedented tools for organizing and manipulating information. Now we have AI, specifically transformer models that process information using mathematical techniques called embeddings, ways of representing concepts as points in multidimensional space, essentially creating sophisticated maps of meaning and relationship. This represents perhaps the most powerful information organization system humans have ever created. AI can certainly assist us in grappling with vast amounts of information, but how will we choose to use it? Steve Jobs once described computing technology as a bicycle for the mind, a tool that amplifies human intelligence rather than replacing it. That's what code fundamentally is, and what AI has the potential to become. The question isn't whether these technologies will change how we think, but whether we'll use them to think better, deeper, and with greater wonder about the world around us. In this blink to The Magic of Code by Samuel Arbesman, you've learned that code serves as the building block of our digital universe, enabling infinite creative possibilities through abstraction and collaborative development. Programming languages have evolved from binary machine code to diverse expressive tools that translate human ideas into computer instructions. We face a choice: use AI and computing to amplify human intelligence, or let them replace our capacity for wonder and creativity. Okay, that's it for this blink. We hope you enjoyed it. If you can, please take the time to leave us a rating. We always appreciate your feedback. See you in the next blink.